Right, morning everyone. It's 3 past. We'll start the session today. I did indicate that we'll be discussing 2.4.4 up to 2.4.7. So finishing up with what we're doing. I do want to change up what I'm going to do for a number of reasons. I would like to discuss a few things that, a lot of questions were raised about in yesterday's stat. And then I would like to know why the majority of you feel that you are okay with some of the theoretic models or driving some of the theoretical models and not so much with others. Okay, so the ones that haven't responded to that, please do so. Information is actually quite valuable to me. In any event, first things first. The almost all groups had the question, what or why does the textbook remove rho in some cases and some cases not for the flow relationship of a valve? And I would quickly want to address that. Just waiting for my screen to share, and we'll start with that one. Right, so there's this thing, CV. I would like your responses on this, please. Dimensionless number, correct. Independent of any of the characteristics of the fluid, correct. Answers in chat, please. If you are a little bit lost of what I'm talking about, it's this equation. Ugh. So dimensionless, independent, doesn't matter. It's very much like, let's say, X, the mass fraction of a, a solvent in a solute, or a solute in a solvent, or whatever. So we all know that is dimensionless. That is absolute nonsense. So it is incorrect. So even X, let's say X of A, it's got units. And for the simple reason, it's got units because it's got mass or moles, doesn't matter, of that over moles, let's say, of everything, total. And for that reason, that is not a dimensionless value. If you see it as a dimensionless value, which in some instance it is, because that is the dimension, that is the unit, but it's the unit in respect of something, in respect of a specific component. So be very careful when you consider dimensionless units. The same goes for CV. So if we discuss CV, does anyone know where it comes from, what it is, and how it's determined? Let's ask that question quickly, and I would like to get your responses on that as well. So you can tell me how it's determined. Okay, that's the wrong CV, by the way. You are talking about specific heat in that case. One considered at constant pressure, the other considered at constant volume. The CV we are talking about is that relationship between the resistance of some piece of equipment, whether it be a valve, orifice, plate, elbow, T, and that constant value relates the resistance to the flow. Jessica, that's perfectly correct. So if, let's say, I am company valves are us, I built this valve and that drawing. Now I need to indicate to my clients what is the valve characteristic. So I need to determine that value. So we use water, and we vary the flow rate of the water. So we vary the flow rate of the water, and we find some characteristics regarding the resistance of that. So CV is not the resistance. The resistance is the one that's usually below the line. So it's actually kind of an inverse, but it's not 100% the resistance only. So I don't want to put CV here, but let's call it something else. It is some form of a characteristic of that valve, which it imparts on the fluid flowing through it, and that causes that delta P, the pressure drop through the system. Now, first thing that you should note, we are using water. Water, obviously, because it's one of the most abundant things that, or liquids that we actually have around. So it's easy, it's cheap, it's everywhere. We can use that to determine all of these characteristics of our equipment. But water has got a density. Water has got a viscosity, and the CV is not independent of those two. It will have some form of variation depending on a different viscosity, depending on a different density. It's not necessary that that is now a function of some other input. We can assume it as constant, but the fact of the matter, it is not dimensionless. It has got some dimensions which refer to the specific set of parameters used to determine that CV. So that CV, if you determine it, let's say for canola oil, you're going to get different values for CV when you relate that to the same experiment done with water or mercury, let's say, because those things act upon that valve in a different manner. There are different adhesion forces against the wall body and after the valve body, the valve stem, those sort of things. So it is not 100% constant. However, it doesn't change a hell of a lot. Now, where the confusion comes from is our fancy textbook either using this equation or this one, and it seems like they're doing that willy-nilly. Let's feel like we're dividing by row, let's feel like we don't divide by row. From this point onward, forget what is in the textbook in that regard. In any question that I will ever ask you, to avoid any form of confusion, I will provide you with either the equation, and it will most probably look like this, not CT, SG, damn it, SG. So the reason for that is because this value has been determined for water, the SG already relates that to some extent with water, because the SG of a liquid at least is obviously determined for the standard temperature and pressure density of water, which is 1000. Or not, can't remember. Normal temperature pressure, standard temperature pressure, whichever one. But in any event, the value, the SG, relates that, and that will solve your CV problem in this scenario. So please note that CV is not 100% dimensionless. It does have dimensions, and it is dependent on a number of things. It doesn't vary too much, but if you need to work accurately, you need to compensate for a change in viscosity, you need to compensate for a change in density. In some instances, you'll have to, so in some instances, you can assume it to be a function of temperature, because viscosity and density will also change with temperature. Don't ever do that for CPN, but just know about the fact that CV is not something that is firm and fixed. For a valve, it will be this value. It's something that is actually experimentally determined. They do it for a range of flow rates. If you use it for something totally weird, like a non-Newtonian flow or something like that, then it will change. It's not going to be the same. And in any case, this equation, if I'm not mistaken, doesn't hold for non-Newtonian, but regardless of that. So does this clarify this issue a bit? Jessica, that is exactly what it is. So we know something like that. So there's some form of a direct relationship. We don't know exactly what that relationship is. There's some form of a relationship, but it's not, zero isn't zero. So if this one is zero, that one is zero, but in any case, but obviously the endpoint, the maximum value or something, isn't exactly the same. So we need that little bit of a fudge factor. And the only thing that CV is basically a fudge factor to get you to the right answer. So for a valve, let's say we are using a Cobra, really well made garden tap, that CV value is 10. If we use a Chinese one that is very similar, it looks exactly the same, but the internals is slightly less, so say it's more rough on the inside or something like that, that CV value will change, even though the thing looks exactly the same because of the wall friction and those sort of things that change in the specific valve. So if you have an elbow, it can be seen as a similar thing because the change in flow caused by that elbow is dependent on the roughness and all those sort of things inside the physical piece of equipment. So it's basically an adaptation, as you mentioned, that if there was just a pipe, we get X flow rate, but now that we have this restriction, we need to adapt for that to lose that pressure or to adapt for that flow. CV values you will typically, so if you, let's say I ask you a question in an exam, I will provide you with a CV value should you need one. If you are on a plant or something and you specify a valve, you go to the manufacturer's website, open up their downloads page or product page and find that specific valve, and they will provide you with a table or a graph of that valve characteristic. I am very quickly going to see if I can find the swage lock stuff on this. Hopefully I can. Then I can quickly show you an example of that. Just give me a second, please. Okay, no, unfortunately, I can't find the. I'll post it later on. Okay, so I believe that is now covered. I will post that shortly. I just need to take a screenshot of the poll and remove that because it's obscuring my view. Okay. Ivandre. They are scalable to other fluids, so the density obviously doesn't. So the density varies a little bit. Viscosity, there are relations. So depending on the type of valve, it will depend on how much it will change. So if you look at a high quality manufacturer like let's say Emerson control valves or something like that, the moment you purchase a valve from them, they will supply or they will have documentation, an abundance of documentation available on how that characteristic will change for specific fluids, temperatures, velocities, and all those sort of things. And try and so you've done COP last semester, if I'm not mistaken. Don't know if you still do von Karman's equation, the boundary layer stuff, and all those sort of things. think about that and how that, so the CV value and the things that we are talking about now is strongly related to that. So it's very strongly related to how the boundary layer inside a piece of equipment forms, and eventually how that flow develops inside the system. Now, a second thing that I would like to touch on, I'm not going to touch on it in a lot of detail. I haven't done it in a long time, so I don't want to embarrass myself. But at page 25.3 for liquid storage systems, they mention if the valve is considered to be an orifice, a mechanical energy balance or Bernoulli equation can be used. So remember, so you would have done this in COP hopefully. Bernoulli equation obviously relates to that constant total pressure on a streamline, where we can do that mechanical force balance basically, or mechanical energy balance along that streamline. Now, an orifice plate can be seen as something like that. So it's basically, and I think you all know kind of like the Venturi effect, if we have something like that, some form of restriction, which we can assume to be an orifice plate as well. In such a system like this, we obviously find ourselves with well-developed streamlines in this, and this is why they refer to a valve as possibly being like an orifice plate, because over an orifice plate this is true, or to some extent at least. It's not 100% accurate because you end up with flow like this, and here you would form eddy currents. But for simplicity's sake, obviously, we assume that the orifice plate behaves in such a manner that we can apply the Bernoulli equation. In the case of a valve, because the geometry is a lot different, and in most instances your valve body would look something like this, where this would be a separation between the inlet and outlet. Not perfectly drawn to scale, but regardless. And here we have our valve stem that can go up and down. So this plugs this hole in there, and you can obviously see we won't have properly developed streamlines going through there, similar to that of an orifice plate. This is going to be extremely turbulent, a lot of nonsense going on here and here as well. So you can't really assume it as something that would be valid for assuming the Bernoulli equation. In the event of a gate valve, where let's say a gate valve that is fully open, you have this entire surface or volume that is open to that, and your streamlines develop more properly. So that can be assumed as a, let's say, as an orifice. So some form of a restriction, but doesn't hamper the streamline formation. So just so that you know that I'm not going to test you on something like this, so don't worry. We're not here to develop all sorts of funky stuff with mass and momentum and energy balances. I just want you to know where these things come from to avoid a bit of this confusion that seems to be growing among you. Does that cover that point? I hope. Before we move off of the topic of the valves, just to reiterate, we will be using this in all instances, or just a linear version for case of linear. So obviously this is your square root valve, linear valve, but it is some form of a relation. And if I provide you with a CV, I'll provide you with units, and you'll be able to notice whether it's SG or rho. Okay, then this other thing. Hopefully all noted yesterday that GC is obviously that relationship that the stupid Americans use to relate their stupid unit system to force and mass and all nonsense like that. So that pound force crap that you dealt with in CIR when you did unit conversions. And that in that instance, we also use this GC thing for us South Africans who are sensible and use the SI unit system. You will not be faced with that GC nonsense. Don't worry about it in your test exams. Don't include it because it's incorporated in our unit system. And wherever you note that GC in the textbook, just remember that it's an American nonsense unit system, and they have these stupid things that they need to deal with because their lives are obviously not complicated enough. So we'll always be dealing with SI units and ensure that the only thing you need to ensure is that your units are consistent. So whenever we have this sort of scenario, when we have to deal with something like this, and you, let's say, end up with this form of the equation, something like that, always just ensure that these units are consistent, because this is a force balance, and you need to ensure that the newtons are related to newtons and that you don't work with megapascals or kilopascals or mix of the stuff. Just always remember what the units of rho GH are. Okay, so please remember that. And by the way, even though this module is not called process units, I will always mark units. If you don't provide units, answer is incorrect. Because a value of 10 doesn't mean anything. A value of 10 liters per minute or cubic meters per second or something like that, that is meaningful. The value 10 is not correct. It's incorrect. So don't ask for half a mark or anything like that. No units, no mark. And I will never stress that again. You'll just see it in the test, by the way. Righto. Okay. So we kind of dealt with this in terms of the G over GC term, not that. So as I mentioned, and I honestly, I hate the fact that they say that the CV is dimensionless. It is not. It does have units, even though they all cancel out somehow. But it does have units, and I mean, if you say it's dimensionless and something like that is perfectly fine, because now we can just multiply by any number that we really want to. That is not the case, because G over GC is also not dimensionless. It still has got that relation between something and something else. And the something and the something else is two different things. So yeah, but don't worry about this. We're not going to handle these sort of things. Obviously be aware of it, because industry is riddled with imperial units because of the fact that a lot of the equipment is manufactured in America or England and so forth. So they have that unfortunate disability. The only imperial units that you will ever find in this module is this range. Anyone tell me what this range is? Just out of curiosity. Any idea? I'll give you a hint. It's closely related to this. Come on, don't be scared of being wrong. Give me an answer. What are those two? Oh, don't worry about the units itself, but what's that range? Okay, Zander, on the right track, but not 100% correct. So a lot of the control valves that we use in industry are pneumatic control valves. So there's an air pressure signal on top of that diaphragm, and this air pressure signal is always in the range of that 3 to 15 psi. So obviously, if we convert that to a kPa or bar unit, it's obviously going to be some what you call it, decimals after that. So it, because of the fact that it's standardized by Americans and so forth, 3 to 15 psi will be used for all pneumatic valves, or the pressure range of all pneumatic valves. And then this 4 to 20 milliamp signal would be, I assume you might be more aware of that, because that is the industry standard for electronic signals. Be aware of the fact that there's this as well, sometimes given as this, or those are used sometimes. It is not the greatest. And so obviously volts and milliamps, roughly the same thing. They are related to one another. Only problem with volts, and this is a question I like in CPB, problem with a voltage signal, you've got voltage drop over lengths of wire. So as a wire gets longer, obviously the resistance goes up and the voltage drops because of that resistance, whereas the milliamp signal stays relatively constant. Other issue of this is that zero value. If you have a power failure, you have a value of 0. So you're measuring your data acquisitioning system sees a 0 and it's like, okay, my 0 value for this flow rate is 2 liters a minute. So currently we are having 2 liters a minute. Meanwhile, that is 1,000 liters a minute because the power supply is damaged and you get a 0 voltage signal out. So that is why this is the preferred signal range. Miller, so yeah, that pressure range has got nothing to do with the process. So if we have something like this, let's say this is enclosed and this is at a pressure much higher, but we have a flow and then a control valve. So the control loop that controls this pressure signal, and I'm already doing this wrong for your learning potential. So this measuring instrument, this provides a milliamp signal out, which is just the standard range. So if it's in the range of 4 to 20 milliamps, if the apologies, if the range of this pressure could be between 10 bar and 1 million, just to be interesting, a value of 4 milliamps relates to 10 bar, a value of 20 milliamps would relate to 1 million bar. And this signal then, a 4 milliamp signal, if it's I'm not going to confuse you with this, if it acts similar, damn it, I wish I had some water with me. We get to direct acting and reverse acting at a later stage, but in any case, let's say it acts like low value to low value, then the pressure signal that indicates to this control valve we need to be at the lower limit now will be 3 psi. So that's just the pressure that is provided onto the diaphragm of this valve. And let me quickly show you on this valve that I have with me. So you will be able to see, okay, so this is obviously our process part. This portion is not connected in any way apart from this fixed stem, which is a solid piece of metal. This is obviously solid, so none of the pressure or air in here mixes with your process. The pressure that I'm talking about is this signal that comes in here. And you'll see this black line here is a diaphragm, and in this portion there's a spring that contains that, or that provides force for pushing it down. When you provide that standard milliamp signal, pressure signal, it pushes the diaphragm up, which extends this and opens the valve. So I'm talking about this standard signal, and don't think you'll be able to read, let's give it a go, but on this nameplate right at the top, you'll see there's a PSI or pressure value, and that value is 3 to 15 PSI. Okay. So I had to say that because if I ever mention 3 to 15, then you'll all be like, oh, but you said we'll never use imperial units. But in any case, that's how that part works. Is everyone happy with flow through a valve? Where that equation comes from, how we will be dealing with it in the remainder of this course, and how you should go about calculating. I think most of you had the deriving the model correct. It was only that issue relating to rho and G over GC. Okay, so I'm going to put up a poll because I want to know that information. And then quickly in answering Miller's question. So the valve I just showed you, you saw that the diaphragm portion was relatively small on a, give me a second. So I'll be sharing my video quickly again. So here we have a valve which is not much bigger at the bottom. So it's a 1 inch versus a ½ inch orifice for the flow. But you can note, obviously, the valve is substantially bigger. This can handle a lot more pressure on the process side. Because of this circumference of the area of the diaphragm portion. So the air supplied to it can provide a greater force for the valve to open and close, meaning that you can run the valve or operate the valve at a higher process conditions or process pressures. So the diaphragm pressure doesn't matter. It's basically just the physical configuration or setup of that valve, how that changes. In any event, while this is close by, we'll at some point in time talk about transducers, which changes that pressure value to the milliamp value to the pressure value, and that transducer is this thing here. So this actually is provided with a milliamp signal, an electrolytic signal. Air is supplied to it, and it regulates the air which comes out here to operate the diaphragm. And then obviously some pressure on top of this one pushes the valve stem down, and a spring return which is contained in this portion. In this portion here, that spring obviously pushes the valve up, and that's how a basically a control valve works. Just give me a second again, please. Right, so spent a lot of time on that, but I hope that you have a bit of a better understanding on how that works now. In any event, something that I would like to know, correct, because the force exerted on that, because remember, if you have a So it's not necessarily just the upstream process, but it's also the downstream pressure that determines that. Because if you have a direct, not a direct acting, a air to close valve, if there's a chance that your downstream pressure can increase, then it needs to have force exerted on it such that it overcomes that back pressure, so the valve doesn't leak. So there's a number of things related to the valve, how it operates and how it's manufactured, that actually determines the actual working pressure. But in any event, yeah, to some extent, the diaphragm area will determine the maximum pressure of that valve. Okay, I'm happy to see that most of you are happy with the liquid storage systems portion of the work. Regarding the question or the poll that I had up earlier this morning, the question relating to some of the models are fine, others aren't. Are any of you referring to 2.15 was extremely difficult, but all the others was really easy? Is that more or less where you are struggling with, or is it something specific that you are struggling with regard to the models? I got a comment that we are handling a lot of theory in class, but not doing any form of exercise in terms of deriving these models. And it's a very difficult thing for me to comprehend, because at the end of the day, I am not here to explain to you how to derive a model for diffusion or something like that. That is something we teach you in mass transfer. And for the kinetic part, obviously, we teach that in CKN and CRO next year. We are here to use all of the information that you get from various other modules. Some of you, the ones that you have done already, some of the ones you are still doing now, and kind of relating them so that we eventually can get the bigger picture of the entire process to determine. So please don't expect of me to teach you how to set up a model for a specific energy balance or for a specific momentum balance. That is not the purpose of this module. The purpose is to relate that eventually to a set of equations and a dynamic model of that. So in short, what I'm trying to say is that the practice or the understanding of that is kind of either someone else's problem or your problem, depending on whether you've done the module already or not. I will try my best to assist you with some of that, but a lot of these things I don't come across very often. So let's say 2.15, I neglected to read the entire question. I saw the reaction rate and thought, oh, well, it would be good to introduce a reaction to the system, and yeah, made a bit of a boo-boo in any event. So if you have comments on what you really need to see, then I will either provide you with what I can, or we will discuss it in class. Another thing, so the guys that were in Josh's group yesterday might have came across this. So he was not 100% happy with the way you are handling degrees of freedom, and I do agree with that. That is my mistake. Sorry, I should have shown you this in the very short lecture that we had on that. When we have any form of a system, so we are going to make up some values. I'm not going to do the entire derivation now, but let's say it's that blending system, or height, or whatever, doesn't matter. The best way for you to determine your degrees of freedom, and yes, this is slightly longer, it's going to be slightly more tedious, but while you are deriving your equations, so let's say you are now setting up your d rho dv dt equals what, and eventually you come out and you say, okay, so I have dh dt equals something, and this is equation 1, and now blah blah blah, 50 more equations, and I end up with a equals pq, whatever that might be. And now I say, oh, I've got 57 equations. Yes, so 57 and variables, I think 50, so yes, 7. It's easy to do with 3, 4, 5 equations and 6 or 7 or 8 variables. It gets a lot more difficult and you're more prone to make errors the larger the sets of equations that you're dealing with. So the better way of doing this, go on, make yourself a table. And number your equations, write the equation. So after you've derived all your equations, then you can go about and say, okay, so I have that one equals blah, blah, blah. In the next column, you can indicate your variables. You indicate your parameters. And it's much easier to keep track of the number of variables that you have, the number of parameters. You can look at all your equations neatly written below one another, go through all of them and determine which are your variables, which are your parameters. Also very important is what state, so whether it's a state variable, whether it's a input variable, output variable. So you can go and say, okay, well, here we have h, and this is my state variable, because it's the one that features in that term. And at later stage, perhaps we have dt or dt. So we know, okay, so t is another state variable. And in here we have parameters a and u, etc., etc. Perhaps that's as, and in this one we have another a. So rather do it like this, rather separate it completely after you've derived your entire thing, write it neatly in a table. I must admit, it's also for me to mark it a lot easier, because it's easier to view it in such a format than to look through 2-3 pages worth of equations to see where you found the correct answer or not. But it's easier for you to keep track that perhaps you made a mistake with this area, which is a cross-sectional area of the tank perhaps, and this one, which is the surface area of your heating coil or something like that. It's much easier to keep track of that and ensure that you didn't make a mistake by omitting an S somewhere, and now suddenly you working with the incorrect parameter. So please rather do it in this. I try to find an example of that. I will do so, and I will post it in Slack just for you to view what exactly we want from that. Everyone happy with this? %. So after considering the information that we try to convey from 2 point whatever to 2.4 point whatever to 2.4.7, I am going to leave this to you as self-study on basically just the assumptions that are made with respect to specific scenarios. So whether we have steam heating, whether we have a heating element. If you have any confusion in that regard, please do let me know. The assumptions are stated. I would try and refrain a little bit from following all of these assumptions always, except if you can prove that that is in fact the case. So for an example, if we make the assumption of page 24, steam heated stirred tank, usually HSAS is much bigger than HPAP. CP will get you just now. So that assumption is a valid assumption. The reason for that is the flow rate of the steam is usually much, much higher because it's gas vapor phase, obviously. Reynolds number is much higher, so you have a lot more heat transfer. So the limiting step is between your stagnant or slower moving process liquid or fluid and the area associated with that, so that convection term. So that's a reasonable assumption to make. But that assumption is not necessarily reasonable when you notice that the flow is, let's say, a double conduit heat exchanger where your process fluid is actually moving at a much faster rate. Then you will have to delve deeper into that and determine whether the process side or whether the steam side is actually the limiting one. So try to understand the reasons why these assumptions are made, and then determine for your own scenario whether that is a sensible assumption or not. Last thing that I would like to cover quickly is page 28, stage system, three-stage absorber, equation 270. So for example, a linear relation is often assumed for the equilibrium between the vapor and the liquid on that stage. So I think you are dealing with mass transfer now, or perhaps you did it last semester, can't remember. You should have noted there that there are numerous different relations for or equations. You know, each and every guy makes up his own set of equations for that. I can provide you with any of those. So I can provide you with a relationship that is, let's say, some form of a square root in there. So don't focus on the exact equations that are given in this textbook. Understand what is provided to you in the question, and understand what it is relating. So the important part from all of these subsections are, how to tackle where does this part come in. So obviously, if we have a vapor liquid equilibrium, it's obviously in some form of a component balance where you have to introduce this, because you have change of that system throughout the process. And obviously, specifically to stage systems, always remember that you need to do a balance on a stage. You can't, obviously you can do over the entire vessel, you will do your complete mass and component balance, but you need to determine the changes in the vapor and liquid per stage. So any specific questions on content from 2.4.1 to 2.4.7? We're not dealing with fed batch bioreactors. I don't like bugs and stuff like that. Tomorrow we'll be discussing process dynamics, and we'll start to introduce you to study theme 2, where we are handling simulations of these systems. We will also continue to derive some of the equations, and then import quotations to a computer system like Python or something else for you to do some simulations on. To answer your question, CP, Sepia, whichever you prefer, the content, so chapter 1 and chapter 2 that I uploaded, I did upload only for a limited time. It is now almost 2 weeks. You must please get your hands on a copy of the textbook. If there are any issues related to availability of textbooks, please do let me know. Unfortunately, the bookstores obviously close to campus will have, because they know about us using the textbook. But other than that, you must please get a copy of the textbook. I may not share all the chapters with you because that's copyright infringement. I will get in trouble if I do that. So for that reason, it was removed. Right. I hope you learned something today. I am going to try a few different approaches for specific content or themes, because after a few attempts, it seems like you are still struggling with a lot of things, but I believe that you don't struggle with deriving the equations. I believe that you are struggling with the actual, why is there rho, why isn't there rho sort of things, which is not actually related to the derivation of theoretical models. Enjoy the rest of your day, and we'll see you tomorrow morning at 9:30.